Hello, everyone. Today, I'm delighted to present our recent work on high-precision self-supervised monocular depth estimation with rich resource prior. This research was conducted by myself, Wencheng Han, and my supervisor, Jianbing Shen, from the University of Macau, China. Here is an outline of our presentation. We will start with an introduction to the problem and related work. Following that, we'll dive into the details of our proposed method, covering its various components. We'll then present our experimental results and conclude with a summary and future directions. Depth estimation plays a critical role in many computer vision applications, such as autonomous driving. Traditionally, monocular depth estimation relies heavily on rich resource inputs, like high-resolution images and multi-frame sequences, to achieve high accuracy. However, these inputs are not always available in real-world scenarios. Our work proposes a novel method that leverages rich resource priors during the training phase to improve the accuracy of depth estimation from single low-resolution images during inference. Our proposed method is called the Rich Resource Prior Depth Estimator, or RP or depth. The core idea is to use rich resource inputs during the training phase and leverage the learned priors to enhance the depth estimation from single images at inference. The pipeline consists of an upper branch for high-resource guidance and a lower branch for the low-resolution single-image model. Here is a more detailed look at the pipeline. During training, we use two branches, one for rich resource inputs and one for low-resolution single images. The rich resource branch generates high-quality features and depth maps, which are then used as priors in the low-resolution branch. This allows the low-resolution branch to learn from the rich resource data effectively. A crucial component of our method is the prior depth fusion module. This module performs two types of fusion: pixel-wise fusion and depth hint fusion. The pixel-wise fusion fills in missing information in low-resolution images using corresponding rich resource data. The depth hint fusion captures prior information from the entire reference dataset in an attention-based manner. We use a rich resource guided loss. This loss function consists of two parts: the viewpoint reconstruction loss guided by rich resource inputs and a consistency loss guided by the predictions of the rich resource model. Additionally, we use an auxiliary loss to guide the optimization of the affinity matrix used in the prior depth fusion module. To reduce the computational burden of searching for reference features during inference, we developed an attention-guided feature selection algorithm. This algorithm uses attention mechanisms to identify and select the most representative features from the reference dataset, significantly reducing the computation required while maintaining or even improving performance. We evaluated our method on several benchmarks, including the Kitty, Make3D, and Cityscapes datasets. We compare our approach using various metrics such as absolute relative error, root mean squared error, and accuracy thresholds like delta 1.5. The results demonstrate that our method significantly outperforms state-of-the-art models across different datasets and resolution settings. On the Kitty dataset, our method achieves substantial improvements over existing models. Notably, our approach outperforms even the models that rely on high-resolution, multi-frame inputs. This is because our method effectively captures the prior information from rich resource inputs during training and uses it to improve the performance of single-image depth estimation. We also evaluated our method on the Make3D and Cityscapes datasets. On Make3D, which is commonly used to test generalization to new environments, our method outperforms all competing methods. Similarly, on Cityscapes, our method demonstrates superior performance compared to numerous advanced models, solidifying its robustness and adaptability. We conducted several ablation studies on the Kitty dataset to evaluate the contributions of individual components of our method. We found that integrating prior information from rich resource data, applying our feature selection algorithm, and using our proposed loss function all significantly improve performance. The best results are achieved when combining all these components. In conclusion, we've introduced a new method for self-supervised monocular depth estimation that leverages rich resource priors during training to improve the accuracy of single-image depth estimation. Our approach achieves state-of-the-art performance while being applicable in scenarios where rich resource inputs are not available. Thank you for your attention. I'm happy to take any questions you may